So what we did, well, we started with some motivation, then we started describing the well-dominant Witten model for global AdS3. Then we went into the classical limit, which corresponds to the case where we take the level to be very large. And we looked at the geodesics. And we tried to identify not only the particle geodesics, but also the short strings and the long. So now I want to, if there are no kind of leftover questions on this, I want to move to a kind of language that would be a bit more useful in order to look at the spectrum of the CFT, the normalizability conditions, the correlation functions as well, and so on, which is something we usually do in CFT2, which is to go to, or CFT in general, which is to go to Euclidean signature. Okay. So for that, we had the Lorentzian AdS3. And if you remember, this was a matrix which looked like this. Where t is the time coordinate, rho is the radial one, and y is the angular one. The boundary here is at rho going to infinity. Okay, and we also had some a bit field. And so now what we want to do is we want to go to Euclidean AdS3. And further do a useful change of coordinates. So the idea was it will be to take t to minus I times the Euclidean time. I don't want to use tau here or something like that because I tend to use that for the worldsheet coordinate. We're also going to go to Euclidean for the worldsheet coordinate, so that for that I'm going to use z and z bar. And I'm going to define two new coordinates, which are going to be gamma, defined as e to the tau p minus iy, hyperbolic tangent of rho, and phi, which is minus the Euclidean time plus log of cos rho. Okay, and in this coordinate, kind of the important comment is that now the boundary is at phi going to infinity. And you see that when I do this, I also get that in this region, so in the region of, let's say, large rho and large but constant rho, then the map I'm using here for gamma is basically E is the exponential map, right? And so this means that I'm going from the cylinder topology in the boundary to the plane, right? The usual transformation. Okay, so when I do this, what do I get? I get metric which looks like this. B field which looks like this. And so, as I was saying, the boundary is at pi going to infinity, and it's a plane or a sphere if you want, if you add the point at infinity. But I'm using flat coordinates there. Okay. The fact is that as it happens, or almost as it happens with AdS3, this manifold is almost a group manifold, and this means that we can still use the Wassermann-Witten formalism for this. It's not exactly a group manifold. This is what's called the coset space. It's called a hyperbolic plane in three dimensions. And it's a coset space because you can find it by doing this. Okay? So this means that we can still use the Wassermann-Witten formalism, quote unquote. These are known as coset models, or equivalently, you can take them to be gauge Wassermann-Witten models. Okay. And how does it work? What I need to get this in the same way that I wrote the group element in AdS3 in SL2R to get this metric and the corresponding B field from the Wassermann-Witten action. I can do the same with the group element of H3. And the parameterization that I'm using is something like this. Okay. And this you're usually going to see, since we're taking the boundary, if you want the primary coordinates for the boundary, which is vertically a sphere, you're going to find diagrams that look like this. So the particle geodesics that we did last time look something like this. I'm not going to go through the details again in this language. It's basically just a translation. Just going through these coordinate transformations. And for example, if I want to talk about the worldsheet of a string associated to some correlator, say a 3-point function, for example, some long string correlator, I'm going to have something like this. Say I have a long string correlator. Where this is the worldsheet, and it winds, say, omega 1, omega 2, and omega 3 times. Yeah.
So when you start from parameterization with the raw global parameterization of DS3, now you change coordinates and then you go to the concurrent parameterization, which is half a DS3.
Yeah. Well.
So at which moment it was the half?
So in the Lorentzian setting, it's true that it only covers the Poincare patch, but in the Euclidean setting, it's true. It covers everything up to except for the point at infinity.
The coordinates phi and gamma in this picture.
So you can think about gamma as being coordinates, like spherical coordinates, right? And the radial coordinate is basically phi. And
basically is the definition of these W's that you drew?
So this I'm writing just a worldsheet say for what would be the kind of classical worldsheet you would associate to some correlator with, let's call it like this, where these are long strings with spectral flow parameters omega 1, omega 2, omega 3. So we classically we can identify the spectral flow parameter as we saw in the with the solution with global AdS3 as winding, right? So this is what it does. It touches the vertex operators. What are they going to do? They're going to touch. We're going to see today. They're going to touch some points at infinity. That's where you're inserting the operator in the boundary, and omega tells you how many times the worldsheet winds around. Okay, that's the kind of Euclidean equivalent of what we were drawing last time. And maybe one more comment that would be useful is that, again, near the boundary, if I think about a long string with, remember the simplest solution, which was a long string at constant radial distance, right? So just a cylinder basically inside of AdS. The configuration was something like T being omega tau and Y being omega sigma, right? It was a very simple configuration. And this translates in this language into gamma being some constant times z the omega. Okay, where z is the worldsheet coordinate. Basically because these things here appear in the exponent. Okay?
W's have to be integers or?
Yes. Well, as we were discussing with Antoine, kind of classically, if you look at just the zero mode, there's no constraints except that if you look at the physics, I mean, at the level of the zero mode algebra, you don't need to. If you look at the physics, you do, because you need to satisfy the string boundary conditions, right? For example, when you go once around sigma, you want to go you go omega times around y, right? Y is also identified, so you need omega to be integer. At the level that we're going to see today, so at the level of the affine algebra, it's also true already, like algebraically, that this has to be the case. Okay? Fine so far?
The infinity plane you compactify to a sphere, and so you want to see that the both.
Yeah. I'm just well, actually we saw these drawings yesterday in Jakob's journal, Wednesday in Jakob's journal club, right? So I wanted to kind of tell you where they come from, and you're gonna find this type of diagrams in several papers. But I'm not gonna use the diagrammatics too much today. Okay. Okay, so you remember that in this model we had three currents. I was calling J plus, minus, and J3. Right? At the classical level, I just care about the zero modes, and this gives me these are associated with three killing vectors. Of the geometry, and these killing vectors, let me use the same name J for killing vectors, even though the J's are usually used for the one form and so on. It's just a dual vector, dual killing vector. So in this language, we simply have these expressions. This looks very simple, like the following form. look like this. So you already start noticing something here, which is that what do we expect? We expect to have, so we are in AdS3 or the Euclidean version of it, we expect to have a Virasoro symmetry in the space-time theory, right? And you already see that these operators start looking very much like the differential realization of the global modes of the Virasoro algebra, okay? So this is going to act very similar to the Virasoro modes, the space-time Virasoro modes, global ones, if they act on a function say some vertex. I'm going to use V for the vertex operator in general, but in this case it's just the classical limit. So in this case it's just a function of the coordinates on the global on the Euclidean AdS3 on H3. So if I take this to be some function of these fields, these coordinates, target space coordinates, that looks like I'm going to have an index J that looks like some function of gamma and gamma bar, okay, plus an exponential in phi. Okay? Why? Because if I have an exponential in phi here, I get some j factor, some minus j factor here, right? This is going to become minus j. This is going to become minus 2j. Oh, I have a gamma here, sorry. I forgot about that. And I have this annoying term here. You see that if this was not here, right, this would really look like the Virasoro generator, right? I have minus gamma divided by the derivative with respect to gamma minus j, and the third operator, the L1. But this term is annoying. The important thing is that this term disappears if I'm close to the boundary, right? Because the boundary is at phi going to infinity. So near the boundary here, I can ignore this term. And then gamma bar doesn't appear anywhere. So in that sense, I can think of these as holomorphic operators, right? And I will want to identify. So in this sense, what I want to say is that
Capital F is like supposed to be the primary of the space-time CFT somehow, or what was the
no, not exactly. Here I'm just saying that if you take this and you act on a function of the coordinates which is factorized like this, you act in the usual way in the differential generators of the global Virasoro algebra. But what's going to happen is that when I go into the worldsheet theory, to the quantum theory, the vertex operators are going to be written like something like this, where now phi, gamma, and gamma bar are going to be fields. Right? So I'm going to have some powers of gamma and gamma bar in front and an exponential in phi. That's what I'm saying. But it's not. I'm not factorizing space boundary operators in any way. Actually, when we go to the worldsheet vertex operators, the boundary ones are going to just be there by integrating over the worldsheet coordinates. That's
You're using the word Virasoro, but in this case, just this global.
So yeah, I'm saying the global Virasoro.
I mean,
Yeah, it's just a set form.
SL2 are not global Virasoro, right?
Yeah. Okay. Maybe I'm misreading the name. Let me just say that.
I just want to make sure when it's different.
Yeah. So all I'm saying, let me say it in equations. I want to identify this, this. I'm using this funny L because I'm keeping the usual L for the worldsheet Virasoro generator. And this. So yeah, this is all I'm trying to say. Yeah, maybe global IPFT2. It's not a particularly useful name. So this is gonna hold if I do two things. One is if I'm near the boundary, right? And second is if in some way I can identify gamma as the boundary coordinate, right? These are the differential derivatives, and usually here this would be, I don't know, x is the boundary coordinate, right? This would be dx, the sign is off, it's in y. You have dx, x dx plus j, and x squared dx plus x 2j, right? So classically I can identify this, and this makes sense because gamma and gamma bar here are the coordinates of the sphere, right? At the quantum level, it's going to be slightly more complicated because gamma is going to become a field, right? So I cannot really take a field to be the coordinate on the boundary. And we'll see how this happens. But at the classical level, the analogy works perfectly.
Function F to be holomorphic to gamma. You also get this notation without having to be near the boundary, right?
Yes.
Does that mean?
Well, the issue is that, as you're going to see later, in like a couple of minutes, it seems that you can take gamma and gamma bar to be the holomorphic and anti-holomorphic coordinates on the boundary, but at the quantum level, that's not true. Again, when I write in a second the action of the Waterman-Witten model of the Cosset model, it's not true that gamma is going to be a holomorphic field. So in that sense, I can't really say that that I identify directly with the holomorphic coordinate, and that if this is not here, I identify it as the holomorphic in the sense of the boundary coordinate, which I'm going to end up calling x. But what is going to be true is that near the boundary, gamma is really going to be a holomorphic field.
There's no independent physical meaning to this emergent SL2R. Not near the boundary, just have some f of gamma, but not gamma bar. Yeah, I think this is a bulk thing. Is this a meaningful thing or not?
Not as far as I know. There might be a
ZZ worldsheet coordinates or in the
I was just making sure term in the green box down there. I'm saying you kill it if it's just gamma. That's all.
It can be useful for. I never used that way of thinking about it for anything, but it might. I mean, it's true. But
This function of gamma only should be you like to have single validness also. So you want to have single validness. As soon as you have gamma bar, there is no issue of single validness. But if you have a function of gamma, then you won't have my choice as a function of gamma.
It would otherwise be highly constrained, I guess. Just like
Well, no.
so we're gonna see in a second what the kind of wave functions are going to be, and these are not factorized in gamma bar. Okay.
Just one more comment. I mean, this way of thinking is very much reminiscent of if you have only thinking the language of long strings. Because long strings, they kind of wrap the boundary, and the worldsheet is like almost sticking to the boundary. If you the bound state that lives deep inside, they are not captured by this equation. For that, you have to go to this whatever this called the x bar coordinates.
Yeah, of course. That's why I'm saying this is almost the boundary coordinate, and this works only near the boundary. So far, it's an analogy in some regional place. But it's not the final story. Okay. So if there are no more questions, we can now actually move to the quantum theory. So I don't know using numbers, but this would be a second part, I guess. So if you take your group element there and you plug in the kinetic term of the Watomino action and the Watomino term, then what you get is this action. So this is the kind of gauge Watomino with an action or coset model. What you get is something like this. Very simple. Okay. So now again I'm using complex notation also for the worldsheet. I have Z on Z bar and D on D bar of the derivative bar. Okay. I'm promoting the quantities gamma and phi and gamma bar to be gamma of Z Z bar and phi of Z bar. Okay. So this is the action for the model. However, this is not a particularly useful action as it stands. And for looking at the classical equation of motion and so on, it's useful. But for looking at it in a more kind of traditional way of thinking for the CFTs or for CFTs with the Lagrangian, I would like to have a more canonical kinetic term, right? I want to remove this exponential from here. And to do that, what you can do is you can rewrite it in what is known as the Wakimoto representation. Where now I'm going to have not only gamma bar, and phi, but I'm also going to have two fields, beta and beta bar, right? And beta bar, what they're going to do, they're going to simply be Lagrange multipliers. And I'm going to introduce them in such a way that I get a nice kinetic term for my model. And what this does, and also just to be clear, now I'm going to, I want to do this to get canonically normalized field, so I'm going to reabsorb this k inside everywhere. I'm going to take phi to phi over square root 2k. And the beta you would naively use as a Lagrange multiplier inside here. You then normalize it with a 1 over k, right? And what you get from doing this is an action which takes this form, 1 over 2 pi, the integral of 1/2 d phi over pi plus beta d bar gamma plus beta bar d gamma bar. So those are the kinetic terms, right? In this sense, what I'm getting is what is called a non-compact scalar, and then I'm getting a bosonic beta gamma system, like the canonical one in the big yellow book. And then there are two more terms. One term is the actual term. I need to rebuild this if I integrate beta out, which takes the form beta bar e to the minus square root of 2 over k minus 2. Right? And then I have one more term, which looks like this. Okay, so first for this term, you see that if I integrate out beta and beta bar, right, and if I undo this change of this rescaling, I get that beta is proportional to d bar gamma, right, and I get an exponential factor, and then I rebuild this. Okay. Actually, there's an interesting point here. So this is the interaction in the canonical way of thinking about it. And there's a term here which is this -2, which is the same -2 that appear in the, for example, in the energy momentum tensor that I wrote last time. That is actually a quantum correction, right? So it's not, if I integrate this, I get exactly this with this rescaling only at large scale. At arbitrary values of k, I have to add this -2 here. And then I have another term, which you can see it in different ways. This arises kind of the CFT way of thinking about it is that, or the path integral way of thinking about it, that arises because in the path integral, when you do this, when you integrate in this beta, you have a change in the measure, and this change in the measure generates this term here. Another way of seeing that is that you need this model to be actually conformal at the quantum level, and for that you need this thing here. So you can see it, for example, by looking at the beta functions. You can see it in another way by looking at the gravitational equations of motion in space-time, right? It's the same idea, the usual thing. Or the kind of fourth way to see it, or kind of a posteriori way to justify it, is to look at the central charge of the system, what it gives. Okay? And that's what I'm going to do in a second. But so far, this is just a background charge. For phi. And it takes the value q phi equals minus 1 over square root of k minus 2. So I made a beautiful choice of conventions in the first page of my notes, and I ended up with a minus sign here and a bunch of square root 2 factors everywhere. So I kind of went all the way to decide to check everything was consistent, and I guess before the final version I tried to take it out, but so far we have to, for now we have to live with it. There are going to be a bunch of this sign and a bunch of square root 2 factors in some places that are going to appear. It's, I think the consistent is more annoying than problematic. Okay, so this is what you get.
If you start from the action in the first line, there is no way to see the k minus 2.
No, it's really at the quantum level. I mean, if you do it carefully with the path integral and the actual measure, you do.
Isn't the action on the first line also supposed to contain what does it mean Witten term? Because it is a WGW model, or is the action that you wrote?
It contains it. So the d gamma bar, d bar gamma has a symmetric and an antisymmetric part inside of it. It's already there. It's just that it kind of comes together nicely. But
you think these two actions are in the real and the quantum level?
sorry?
The first line. And these two actions.
Yeah, they're equivalent. Yes. Yes. Exactly. Well, one way to see this, what I'm going to write just now, is that, okay, so first of all, the first comment is that the interaction is negligible near the boundary. So again, at phi going to infinity, I changed the positive exponential in phi that I had in the first line for a negative exponential here. So this interaction term you can just ignore near the boundary, right? If you do that, you get gamma and beta as holomorphic fields in that region. And you can think of this, as I was saying, as a non-compact scalar phi graph with a background chart plus a beta gamma system.
I'm confused actually, because if I start second action,
Yeah.
we agree that beta fields are not propagating. Beta fields are not propagating.
Yes.
If I eliminate beta fields, I will get action which is different from the first line.
But you have to do it carefully at the level of the measure of the passing there. Right?
But as soon as you agree that beta are not propagating,
Yes.
there is no problem with eliminating beta fields. I think there is an issue with normal ordering of the when you're writing this action on the first line.
Yeah.
It's financial to five. Is it normal ordered or normal? Not
No,
normal.
the first line is semi-classical, right? The first line in terms of gamma bar, that's a semi-classical level that also receives quantum correction.
This is what I was saying. These actions are not equivalent.
That's what you get if you just write the group elements in the Waterman with an action.
I think that you were saying that the second line includes well, basically loops, one loop.
Yeah.
The second line is quantum corrected. The first line is
Yeah, that's true. But okay, let me. I don't remember exactly the details now for the. Let me go back.
Maybe the second line is correct.
Yeah, the second line is for sure correct. I don't remember exactly for the first one. It's exactly what you get from the Waterman with action, or there's some semi-classical limit.
No, but the question is, even if you take it from the classical level, the question is, what happens if you include quantum fluctuation?
Yeah, I agree.
So the question is, quantum fluctuation will bring you to second line.
Okay.
One loop.
Okay.
And this one loop quickly.
Yeah, you're probably correct. I think I think I never thought that down explicitly, but I have to check. But yes, sorry.
there is difficulty in doing what you are saying at the first line because the second term it's very strongly coupled. Gamma bar is strongly coupled because it's exponential 2 pi. So if you want to do the one loop calculation for that, it's going to be problematic. But it's easier to do it in the working module.
Well, if you use the first line come from the term, I know for sure that one loop corrections will be exact.
Yeah, but it's done in the global AdS, and then you do this Euclideanized version, and then map it to Poincare AdS. So it's not directly coming from the Wisdom-Innovative action. What comes from the Wisdom-Innovative action is the global AdS. But this is Euclideanized Poincare AdS.
This comes from the
Something happening in between.
from the cosset action.
Saying that this calculation also back to this global process.
Yeah.
Okay.
And just 1 second, because this one has a conical singularity at rho phi goes to minus infinity. Global AdS doesn't have that. So there's a big difference between the global AdS and this one.
Okay. But yeah, let me look at the details again because it's okay. So, any other question? So when I do that, in this limit, I can just think of beta and gamma as being holomorphic. So I can just think of the usual OPEs between them, which looks something like this in my conventions, and then phi is canonically normalized. So I get minus log mod z squared. And just by looking at this simple system, you can compute what the energy momentum tensor is, and you get minus beta b gamma minus 1/2 d phi. And then you get a term that comes from the having this background charge here, which looks like q phi over square root of 2 in my beautiful convention. This called phi. So this is just a usual part coming from the kinetic terms, and then this is from the background charge. This R2 here is the curvature scalar on the worldsheet, the two-dimensional one. And from this, you can look at the OBE and compute the central charge, right? And the central charge is just the 2 that comes from the beta gamma system. Okay. Here, well, this happens because it's one of the examples of the beta gamma system where the worldsheet weight of beta is 1, the worldsheet weight of gamma is 0. It's going to be important later on. And then you get a plus 1 from the usual term for the one single non-compact scalar, and then you get, in my convention, this. Okay? And if you plug in the value of Q phi that I wrote here, right? So if you plug in that Q phi is minus 1 over square root of k minus 2, and you do the sum, what you get is exactly 3k over k minus 2. Okay, which is exactly what you should get. It's the central charge that we were talking about in the last in the other lecture. Right, it's the worldsheet central charge. So this tells you that this Q has to be there and it has to have that value at least up to the side. Okay. But you can also proceed similarly to what we did in the AdS3, which is you don't have to buy that. You don't have to know that this is actually the energy momentum tensor just by looking at the action and the fact that these are canonically normalized fields and so on. You can also use the currents themselves. In this context, the currents, which now are a function of z, are realized like this. So I'm implying there's a normal order here that I'm not writing, and you get something like this. Okay. This is a form of the three currents. The holomorphic ones, the anti-holomorphic ones are exactly analogous. And if you plug this in the Sugawara construction, as we did last time, right, you can find that this is exactly 1 over k minus 2 p plus p minus p minus p plus minus 2 directly. Okay? Actually, because of this normal order term here, this computation is a bit cumbersome. It's a bit long. You can find it explicitly in the big yellow book for SU2, where there's an analogous story, it's an analogous Wakimoto variables, and you do the same, except that there's a plus sign here. But you just get exactly the energy momentum tensor that we get just by looking at the action. Okay? Yes.
So your phi is the Liouville field.
Yes.
So you got Liouville coupled to the meta, and meta comes to gamma bar.
Yes.
So what's special about this? Say you start from the action which was coming from Vezomina beta, and you got a very special form of the metal. Let's say K defines central charge with metal. Right?
Yes.
But if I would start from what I would say that I would consider more general action. Just you got some particular meta which describes the gamma bar, but what was special about the original series that led to this particular action? I could start from the very beginning saying I want to consider like two-dimensional series, Liouville coupled to some meta.
Yeah. So in general, what's going to happen is that you always in AdS with global with Lorentzian recursion, you have a direction which is a non-compact direction, right? And that's always going to show up as some type of UV field in your worksheet.
Okay, why it boson? I mean, I could put fermions there.
Yeah.
So what's in some sense you got very special action.
Yeah.
So my question is like why it's so special? Why you go to this particular gamma bar system instead of general one which includes fermions, whatever?
Sorry, I'm not sure I understand.
Normally,
Why do I choose this coordinate?
I consider a general action when you have UV coupled to matter.
Yes.
I don't need to specify which matter. I'm just saying matter which described by some conformal field theory with certain like keep is equal.
Yeah, but this is some particular model, right? I have some geometry I'm trying to describe.
It came from the DS3. So you start from DS3
Yeah.
space, DS3 led you to the.
Yeah, exactly. Yeah. I'm sorry. It's just
This is my question.
I take my geometry. I think about it as a either a group manifold or a coset space, and then I derive this. Yes, it comes from that geometry. Okay. Any other question?
This Washimoto notation is very good for asymptotic analysis, right?
Yes. It's not the exact theory. Right? It is the exact theory. It's not the exact theory if you ignore the interaction term and treat gamma and beta for more.
Yeah, but I mean this exponential minus phi that I'm dropping, like as you are saying, it's Liouville theory, and we know that the ground state of a Liouville theory is non-normalizable, whereas we know that the ground state of the full theory must be normalizable.
Yes.
So
I'm gonna get to the exact theory later. But this language is kind of useful to.
you are saying that to know the central charge, I think it's okay to just look at asymptotic theory.
Yeah, the center charge is not gonna change because of the interaction. But what's not true is that I can write T in this way because gamma and beta are not gonna be hormone.
Yeah, so I see. Liouville potential, I think what you are saying is the Liouville potential, the central charge doesn't depend on the Liouville potential.
Yeah. Okay. Fine? Great. So now I want to ask the following question. I want to make one final result from all of this, which now is going to be kind of a pointless comment, but it's going to be useful in a second, is if you take these OPEs, this realization of the current, and write it as J3, and look at the OPE between J3 and some power of gamma, right? What you get is something that looks like this. Right? So this means that gamma n, gamma to the n, has charge minus n with respect to the J3 current, or if you want J03. Right? This is just a comment for now. It's going to be useful in a second.
From your action, because your action is had one symmetry, right? You had the action which had additional symmetry with respect to rotation of U. So this what you're saying that I could associate with U certain charge. It's this action which you wrote. Right?
Yeah.
So if you rotate gamma bar of some phase, it's invariant. Because you are invariant.
Yeah.
So the G3 exactly measures the charge.
Yeah, it's there's a piece that's also associated to phi, right? What did you write here? It's a combination of what you're saying and some shift in phi. It's not just but for gamma, for the field that you're talking about, this gamma is exactly what you're saying because it has no p with phi. Okay. In general, it's not only exactly that.
Okay, then what shifts gamma and gamma bar are this J plus and J bar plus. That's the U1 symmetry that I think.
Yeah, the beta is the one that is the derivative, but that's just is not the phase. Okay. Just a maybe small useful comment. If you're more used to the beta gamma system, that the ghost system that appears in string theory when you quantize it, that's a fermionic, and so you get a plus here, the minus sign difference in the OP. This one is purely bosonic. Okay. So now I want to ask the following question. From the work. Right? So again, as Max was saying, I'm working first at the level of the Wakimoto representation. I'm working near the boundary. I'm taking gamma and beta as being holomorphic. And what I'm going to do now with that can be done also at the exact level. It's done explicitly in the lecture notes and in the original paper by Cyber, Given, and Kutasov. But I don't know if I'm going to have enough time to do both ways here on the blackboard. So let me do this one, which is kind of a bit more intuitive. And if you have some questions about the exact one, we can discuss them. So what do I expect? I should be able to find, first of all, a Virasoro algebra. So the generator Ln. Then if there is, for example, some arc symmetry or some extra symmetry, right, of the boundary CFT, of the spacetime CFT, I could have some Kac-Moody algebra, say with some index A and some some index number n, right? So for example, in the T4 case, you have the SU2 arc symmetry on the left and SU2 arc symmetry on the right, and these are going to be exactly the modes of that affine SU2, right? And then I have the cross term between them, which is something like this. Which gives me minus n k a and plus n. Right, this is the structure I expect to have. Some Virasoro algebra, some Kac-Moody algebra, and the cross commutators, which will look like this. Okay? That's the goal. But I'm relatively reasonable at drawing this funny L, but very bad at drawing this funny K. There's going to be another K in the worksheet, so I hope it's clear from the context. Okay, so first, we already know that we have the identification that the L0 should be J03, which I can write like this. And the L plus and minus 1 are the J0 minus and plus, and I can write them again like this. Okay? So this is the first part. The second part is, where do I get these modes here? Right? Where do I get the Kac-Moody symmetry, the SU2 symmetry? Well, obviously we know that in holography, for example, the usual way the SU2 symmetry or the arc symmetry is realized is that it's realized in the geometry, right? It gives me some sphere, for example. So in particular, in the case where the internal CFT or the internal sector by which I mean that I have some AdS3 cross S3 cross some internal part. If this internal part is S3 times something, right? Then I have an S3, and then I'm going to have some worldsheet currents, K of Z, and the anti-holomorphic ones, which realize because this is an SU2 assuming non-weighted model at the worldsheet level, and so I'm going to have these currents here on the worldsheet, right? And so again, I can get the zero modes of this space-time algebra quite trivially, because all I have to do is to say that the space-time K0 is, again, it's just identified with the worldsheet one, right? Which I can again write as this. Another question is, I'm going to start with this one because it's easier. The question is, how do I get the ends different from 0 here, right? So for these guys, I need to add something to this integral, right? I'm always going to have to integrate over the worldsheet coordinates because I need something in spacetime which is independent of it, right? So I need to add something here, right? And that something has to satisfy basically three things. First of all, we have, so if I add something here, say I'm gonna propose something like this, with something here, and that something should have dimension, worldsheet dimension 0, right? Because I still want to integrate on that without changing anything, and this is a conserved current, and it has weight 1. Second, it has to have space-time weight what do I want to say? What kind of the simplest way to say it is that I already know what L0 is, right? I know that L0 is this guy here. And I know that, so in particular, if I put a 0 here, no, what did I do? This is 10. I get this, right? So if I do it this way, I know that if I act with L0, I have to get something. This guy has charge minus m, right? But L0 is J03, and I have exactly a candidate here which has charge minus n, right? So the only thing, and also gamma, we said it has weight 0 on the worldsheet. So that's exactly what we need. So the idea is that you simply add this. Okay? Okay, let's see how it works. This is a simple computation. I want to compute the space-time algebra, right? I have this proposal, and I want to see what this gives, right? So I have my definition here. The usual way to compute these commutators in the complex notation is to have an integral on W, an integral on Z, around W, first one around the origin, the second one around W, of my two guys, right? Right? This is exactly what I want to compute. So the first step for this I think it's nice to do it explicitly, is to use the OP between this K and this K, right? We know what the OP is because we know what the worldsheet algebra is. And so this takes the form. I'm going to write it in an unusual order because it's going to be easier to read off afterwards. Again, whenever I have the Z here, this K is the worldsheet K, it's not the spacetime one. Get something like this. And then I get the central term, the second order pole, which is, I'm going to write that K prime over 2. Right, so K prime is this have come from an SU2, say, for example, at level K prime, right? That K prime is the level appearing here. And then I have gamma n and gamma m, but gamma with gamma has no non-trivial OP, right? There are no singular terms. The only thing I have to do is Taylor expand, right? So I get a term which looks like gamma n plus m w, and another term which looks like n gamma n plus m minus 1 d gamma. Right? And I need to do this expansion because right, I need to do this expansion because here I have a double pole, so I have a contribution from that. First, this one, then with this picks up exactly what I need. So this is just a residue on the simple pole, and I get I F ABC KC gamma n plus m w, and then this combined with this to give me something that looks like A prime over 2 delta AB, and the integral is it like this of gamma n plus m minus 1 d gamma. Okay, so here you recognize in this term here, recognize precisely the definition of the mode, of the spacetime mode. So this is just K, I FAB with the same structure constant. Nothing else, right? And here you get a term which clearly, if n plus m is different from 0, is a total derivative, so the integral gives me 0. I have only a contribution from n plus m being 0. I get an n factor here, like this. And I get a k prime and something I'm going to call I, where I is defined as the integral of gamma minus 1 d gamma. Right? So the first part is exactly what I need, and this is exactly the central extension I need. You can check that this guy commutes with everything else, so it's a central extension. But the question is, what's the value? What's this exactly? And so the proposal in the Gideon Kutasov Cyberg paper of 98 or 99.
Where does the factor come from? In the second term, there is n over 2.
There was this n here. I forgot.
It's missing in
Oh,
the
sorry.
last row here.
Thank you. So the idea is, what is this? So if you remember that if you have a classical configuration which winds omega times around around some insertion point in spacetime, for example, For example, in a long string configuration that I wrote, you had gamma being z omega, right? Well, then this picks up exactly omega, right? So this is it. So first of all, if on a classical solution, which is single value, I get the condition that I has to be some number here times, so this number has to be an integer. And also you can check that under the action of the L0, so of J03, this has no charge, right? Because I have a gamma minus 1 and a gamma, so there's no charge there. So this has space-time weight which I'm usually going to call H, as in the first lecture. So 0. And so it has to be proportional to the identity operator on space-time, right? That's why it's a center extension, it commits with everything. And the question is, what exactly is this number? Because I said what the value is for a given classical configuration, but I didn't say what it is exactly. And the proposal in this paper is that I count the number of rings in the background. Okay? And this would mean that, as I said, I started with N1, F1 string, and N5, NS5 rings. Then the proposal of the paper is that at the level of the algebra here, I should identify I being N1 times the identity. Okay? Why would this have to be the case? Well, from the worldsheet point of view, it's kind of hard to see, right? Because the worldsheet is kind of working at very formally, if I'm just doing the sphere, I'm working at formally infinite N1. So I'm not going to see exactly that value here. You can see it for a given configuration, which is a perturbation on top of AdS3, but I cannot count it exactly directly from the worldsheet unless I go to quantum correction, to other topologies. Quantum corrections in the string sense. And so the question is, why does it have to be exactly this? And one way to argue for it is the following, is that I still need to tell you what are the rest of the Virasoro modes, right? And I'm not going to do the full computation here just because it's longer, but the idea is exactly the same. Just a bit longer because now I want to build it from, I cannot just add some gamma n here as I did before, because there's a non-trivial OP between the current and the gamma itself, right? Which didn't happen with K. So you can check that the actual definition that works is precisely this. Okay. Again, it's a bit more cumbersome of the computation, but it's not hard to do. You just have to compute the various OPs between the currents and the powers of gamma. And you'll see if you look at in different papers, you're going to see different expressions for this. The reason is that this expression is only up to a BRC exact term, so you could add something that doesn't change the actual algebra or the effect of these things. How am I doing on time actually? Okay. this time I'm actually where I wanted to stop and not at the end of the full plan. So if you do this and you repeat this computation here with the Virasoro, with the space-time Virasoro modes, you compute the algebra, you get exactly the Virasoro algebra. Let me just quickly write it. And you get a very similar term as before. You get 12. And then you get a factor, which is 6ki. Right? Where this I is the same I that appears here. Okay? And this tells you that the space-time central charge makes perfect sense with what we discussed in the first lecture, because we said it should be 6, well, we said 6 and 5 and 1, but and 5 here is k, right? This is a bosonic model. So this here is k, raise the roll of k, and so you get this if you take the expectation value of I to be n1, right?
Here again, you're not sensitive to the -2 shift in K, right?
Yes, exactly. But so this is the actual. If you are in the bosonic setting in an AdS3 space of size k, if you want. Again, if you want to think in geometric terms, k is large. So
Right.
but this is the actual. There's no k minus 2 that I have to add here at this level. If I work in the supersymmetric model, I do, and I get 6 and 5.
Wouldn't you have gotten this term if you added the n1 units of flux on the AdS3, which are not really?
But you still get, maybe I never tried, but you still get these kind of contributions when you compute the OPs. I mean, you need a definition like similar to this, and you still get this type of things.
Yeah, but what's the number? You're sort of arguing.
Yeah, so again, I agree. If you look at the definition of the B field I gave at the beginning, right? If you write it in terms of the H field, and you assume that I have sorted for that, then I never did it explicitly, but I guess that this should give you exactly this. Yes. That you, in terms of the Wakimoto field, you can take your H field, write in terms of gamma and gamma bar, and write the integral that should give you n1, and it should lead exactly to this. Yes, I have to admit I never tried to do it explicitly, but I guess that's how it should work.
So this is this thing in the supergravity approximation, not even in string theory approximation.
Yeah.
So if you work out the exact analysis, not the in terms of gamma bar.
Yeah, you still get an operator I, which
Yes.
is exact. You don't need to be in a supergravity approximation, and you.
And in the supergravity approximation, and you can show it to be proportional to the sphere partition function.
Yeah.
Which goes as 1 over GS, and GS is basically n1. That's like at 0th order in alpha prime or linear order in alpha prime.
Yes, I agree. But then again, you're not leading order in alpha prime, so you might as well do it in supergravity.
Yeah, but I think what she was asking is that if you can relate it with the flux, right? Yeah. So I don't think you can relate it with the flux. That's.
No, I think you do.
No, because if you add the alpha prime corrections, it's the leading order is n1, and then there is a whole tower of alpha prime corrected states. And we don't know how to calculate beyond the first order. Not states, sorry, terms.
Okay, I never.
The identity of the H1, of the H3, sorry.
So you have to first relate it with the flux, right? I don't think that if you can relate this one with the flux.
Maybe it's because of the Bianchi identity, which is higher order.
That could be even alpha prime corrected. Yes, that could be. Yeah. So this I operator expectation is proportional to the sphere partition function.
Yeah.
Worldsheet sphere. The worldsheet sphere partition function in the supergravity approximation is
the G string.
Is G string, exactly. And G string is 1 over n1 or 1 over n1. G string squared is 1 over n1.
Yes.
N1 squared.
Yeah, there are different ways of arguing for this. I thought this was kind of simple, but of course there are much more precise, in particular in the exact theory, I agree, get. Precise ways to get. Okay. Any questions? No? If not, we take a 10-minute break. So let's continue. Any questions before I go on about what we did? Okay. So we have the space-time symmetries, the affine ones, the Virasoro ones, and now the question is, what's the spectrum of the theory, right? That's the next kind of important question. We're going to do the spectrum, and then the next lecture we're going to look at the correlator. So for the spectrum of the theory, we need to understand exactly what are going to be what are the normalizable states in the model, right? And so in order to say what are the normalizable states, first I have to define what I mean by normalizable, and then I have to actually do the computation. So in the classical limit, again, which is, you'll find it in some places, but in particular for the H3 model, you'll find it in the papers by Teschner. In papers by Teschner in 97, 98, 99, something like that. It's usually called the mini superspace limit. And so what you do, what we said in the first lecture, is that when you are here, you only care about the zero modes of the current, right? And if you only care about the zero modes of the current, you know that the energy momentum tensor simply looks like we have the L0 part, so the L0, and I want the physical states to be eigenstates of this L0. The L0 is simply 1 over k, so I ignore the -2 because I'm in the classical limit, times j plus I may be missing a 1 over 2 here. Okay, but if you look at the interpretation, the classical interpretation of this guy, the Killing vector that we wrote in the beginning, you see that this thing, which is exactly the Casimir, the SL2R Casimir, is exactly the Laplacian on H3. Okay, you just plug in the expression for the Killing vector that we have, and this operator is the Laplacian. So the vertex operator, the model, are going to become, first of all, independent of Z and Z bar. So they're just going to be functions of the space-time, the target space coordinates. And second, we're going to be looking at the wave functions, which are eigenstates of the Laplacian. And so the equation I'm going to be looking at, I'm going to define some functions Vj of x. When I mean x, when I write x, I mean x and x bar, of course. And I'm going to take them to be, so in this limit again, they're just functions, and I have to satisfy the equation that the Laplacian minus the eigenvalue has to be 0. So in my normalization, this looks like k minus 1 over k. Equals 0, right? This guy j is a spin, the SL2R spin. So exactly as in SU2, you would get L plus 1. Here you get j minus 1 with a minus sign in front. So this is SL2R spin. Here I ignore again the -2 because I'm in the limit. And this x, for now, is just a label for the solution. So I'm taking a basis of solutions, which is a continuous one, which is parameterized by x and x bar, right? You just look at this, write down what the Laplacian is, and what you get is that the solutions look like this. There's a conventional normalization, and then you have something which looks like e to the phi, gamma minus x squared, plus e to the minus phi to the minus 2j. Okay? And you see that on these functions, the current acts as follows. J plus 0 acts as dx, J 3 0 acts as x dx plus k, and J minus 0 acts as x squared dx plus 2j x. Okay? This is exactly the realization of the L0 plus and minus 1 in spacetime as differential operators. Again, as I said in the beginning, this guy is identified as the spacetime weight, and this is the exponential in phi I was saying I would have, right? With a correction term here, so this is why it doesn't, in general, it won't factorize in gamma and gamma bar. And again, this tells me that x is labeled x, which from the worldsheet point of view is just a label of the solution, or the spacetime point of view is just a label of the solution, is the worldsheet, the boundary coordinate. Or it will be the boundary insertion point.
Third question.
Yeah.
Was there a 1 over k in the definition of L from the J's? Yeah.
Yeah.
That's why. So it plays no role.
Yeah. I'm ignoring this now, but yes. Okay. So
there should be some k in the v of j. Vj.
yeah, exactly. Yeah. If I try to fix it now, I'm going to make some mistake. I'm ignoring it here.
Was there a way to know a priori that there would be a 2-parameter family of solutions to the Laplacian equation?
Little guys. Way to know before. Never really thought about it. I mean, you can. I'm going to write then.
And I see that those are solutions.
Yeah. I'm going to write then. So the easiest way would be to start with the energy, with states which have a defined energy. So eigenstates of J03, right? Which these are not. And what's going to happen is that you're going to get what we call M and M bar in the first lecture, right? The eigenvalues. And this X is just the conjugate variable to that M in the sense Mellin type transform. It's just that. So you have you knew that you were going to have M and M bar in the basis of eigenstates, and this X and X bar is just the conjugate of that in a sense that I'm going to describe in a second.
I just want to make a comment that I think he wrote the algebra for the J0 plus minus and J3 in terms of gamma, gamma bar, and phi. So there are three variables, gamma, gamma bar, and phi. You can show that you can write the same algebra in terms of two variables, x and x bar. The algebra is the parameterization is what he wrote over there. You take that algebra, you take the algebra of this J, it forms the same as L2 algebra. So that's a way of seeing that it has because the Laplacian you can write it as in terms of J's in some some J bar. Yeah, exactly. That's the Laplacian. So so it should be like a 2-parameter solution at the end of the day.
Yeah. Okay. And just to stress what I meant by gamma being almost the boundary coordinate before, this is what before we had as minus the gamma, right? And the same for the other, except for the anti-paramorphic term. Okay. Okay, so far so good. So why do I say that? So x I want to identify as the boundary coordinate. Why do I say that it's the insertion point? Well, to look at the insertion point, you need to look at phi going to infinity. You need to look at what happens near the boundary, right? And near the boundary, if you just take this function and expand it, what you get is two terms. One is goes like e to the 2 j minus 1 phi. And the delta function, you need to take the limit carefully. This comes from one of the usual limit type expressions for the Dirac delta. Plus a bunch of corrections, and then you have another series of terms which starts with j minus 1 and e to the minus 2j phi and by the way, there's no k here in the sense that the x disappeared because the k disappeared because I'm using the phi that are normalized that I did before, so I normalized with the 1 over square root of k, and that's why it disappeared from here. Okay, plus a bunch of corrections. So in the usual AdS3 language, this is what we want to identify with a non-normalizable mode. I put it in quotes because it's not going to be exactly that for all of the states, but morally, to understand what I mean, this gives you the, depending on the value of j, if j is positive enough, this gives you the leading divergence, right, near the boundary. And so this tells you that near the boundary, that leading divergence is concentrated at gamma equals x. So the state is inserted at the point x in the boundary field, right? So the insertion is at gamma equals x. And then, again, in quotes, this is what I want to identify with the normalizer. But again, you'll see in a second why I'm putting quotes there. Okay, fine. So this is for at least for j sufficiently positive. It's going to be in a second for j larger than 1/2. These two comments. Okay. And now, in order to check which ones are normalizable and which ones are not, I'm going to go to the dual basis, usually called the M basis, and this is usually called the X basis. So in the M basis, I want the basis of states which are eigenstates of J03 and J03 bar. And the way I do that is I take a transform, which is Vj M bar. I'm not writing what it's a function of, but it's just a function of the target space coordinate. And the relation is given by this integral transform over the whole complex plane of x m minus j, sorry, j minus m, x bar j minus m bar, okay. Okay, so these are the energy eigenstates, right? And when I look at what happens near the boundary, what I get It's just a transformation of these two terms. So the first one is very easy to integrate because I have delta function. The second one is a bit more complicated. You get a bunch of gamma functions. So what you get is something like this. Plus correction. And then the second one, as I was saying, it's a bunch of gamma functions. And then the exponential. Plus correction. Okay, so now I really want to use this expression here. Again, this is the, well, it's, you can find the integral that does that. For example, it's in one of, it's in the notes and it's in one of the appendices of the third Malasenao Willy paper on the subject. But what I'm interested in, I think this formula is particularly useful because it allows us to see exactly what the normalizable states are. So again, I'm going to choose the normalization with the usual plain Gordon norm at the classical level. And this takes the form of this. If I have a state norm of dj, say m bar, it's just something like the integral with a number here, which is kind of irrelevant. Then I have the measure, where the most important thing is that I get this e to the 5 factor that was in the metric, right? This is just a measure, and then I get this function. Right? And I have to integrate. Okay. So which type of solutions are there? So you see that I have to take this I have to square this, and I have to add this e to the 5, right? So the two terms I get are going to be of the form, the square of this is 4j minus 1 5. But then I add the e to the 2 5, and this changes this to a half. Right? Is it clear what I'm doing? Yes? No? Yeah? Okay.
Why do you need to go to the MMR basis? You can just the same conclusion can be drawn in the X basis as well.
No, not for the. I mean, yes, but not for the short string. That is it. And the second term is exactly the opposite. So this comes from the first term, and this comes from the second term. And the only thing I care about, yeah.
And why do you have positives? Oh, you put the minus j inside. Okay.
Yeah.
Cross term?
Yeah, the cross term is irrelevant for what I'm saying. It doesn't change because it doesn't scale with 5. I'm only caring about what happens, the divergence can appear at 5 going to infinity. Okay? So what type of solutions are there? So one obvious solution is to have j being 1/2 plus some real number, for some imaginary number, right? So if I do that, what happens is I kill here the divergence, right? Neither this term nor this term have any divergence. That works fine. But I do get, if I did it with j and j prime instead of the same j here, I would get a delta function type of result, right? I would get the, if this was called S, let's say, I would do it with S and S prime, and then the norm of j prime would give me something proportional to this, where the only important part here is S and S prime, right? So these are what are called delta function normalizable states. They're not really normalizable in the usual sense because this has divergence when j is equal to j prime, right? But they are delta function normalizable, and they're something we're used to because these are just the analogs of the plane wave in flat space, right? In that case, this factor here, right? So for the normalizability, I have no condition on m, so I'm not saying anything on m. And since I have the analog of plane waves, one of these factors is the incoming wave, and the other factor is the outgoing wave, right? That's the interpretation of these two modes. And then this, which I call Rj m bar, is exactly the reflection coefficient. So this thing goes into AdS, interacts with whatever is inside, goes out, and there's a reflection coefficient. And in this sense, you're going to see them as they're usually called scattering. Okay, that's my first solution. The second type of solution, which is why I wanted to write it in the embedded, is that normally you would say that if you have j real, right, since one of the two terms diverges when j is larger than 1/2 and the other one diverges when j is smaller than 1/2, then I'm always going to have some divergence somewhere, but this is going to be non-normalizable, except if I sit at very special values of m, right? If I sit at special values of m, in particular if I sit at the poles of these gamma functions here, or at the zeros of these gamma functions here, then I can, if you want, I can divide by this whole thing and I can just ignore the first term, right? So in those cases, I do get something that's actually normalizable, right? Not delta function normalizable. So if I take j larger than 1/2 and m being j plus some natural number, natural 0, or m being minus j minus n, right? Either of these two, then this is normalizable. I obviously need to do the same with m bar.
M and M bar can be different.
Yes. So the number here can be different for m and m bar. If you want the real thing is this. Right? So in the sense of what values can m take, these are discrete states. It's kind of a misleading name because the allowed values for j are still continuous, but these are usually called discrete states because of the allowed values for m. These are states that if you look at the wave functions, they are bound inside AdS. Okay? So these are bound states. And in a sense, they are kind of the representations of SL2R, which are called the principal discrete series, which are more similar to SU2 states. Right? Because what happens in SU2, and I forgot to say here that these are similar to Liouville states. And this is exactly what Grisha was saying. There are some analogs of Liouville states here because I have a non-compact direction phi, right? And if I integrate out beta and gamma, I get some effective theory for phi, which looks like a Liouville theory. And then I have this Liouville operator. This is more similar to SU2 in the sense that in SU2, you all know that if I have some j here and some minus j here, so the representation for the spin j guy is something that sits here. Right? But in SL2, what happens is exactly the opposite. You cover states that are here. So these are the SL2, the SU2, sorry, and these here are the SL2. Of course, it's not exactly the same because in SU2, J can only take half integer values, right? But in terms of where the M eigenvalues sit, or in respect to the chosen value of J, is the same. More or less exactly the opposite. Okay? So these, when I go to the quantum theory, are going to be the principal discrete series. Which are usually denoted as dj plus or minus, right? Plus if you go on this side, and minus if you go on this side. And they have extensions to the full affine algebra. Whereas these states here were the principal continuous series. And are usually denoted as the Cj alpha. Where alpha is some extra index that tells you what are the allowed values for M, which is not related to J. Okay? So in this case, the allowed values for M, so you have some J, which is 1/2 plus IR, and the allowed values for M is alpha plus integral. Okay, so M you still shift by integrals in this sense, but it's continuous in the sense that you can choose any alpha between 0 and 1. Okay? It's separate from, and it's independent of J, which is kind of crucial for the whole construction to work.
Where is that constraint on M coming from?
The constraint is coming from the fact that you remember that the solutions, these ones have some gamma to the M, right? So it's some gamma bar to the M bar. If you want this to be single valued, when you go around sigma, you get this one.
It's not a normalizability.
No, it's not normalizable. It's just single.
Yes. Okay.
Yeah.
So that drawing is for some given alpha.
That one is
No, this is for the discrete series. There's no alpha here.
Okay, but then say, why do you have between -1/2 and 1/2?
You mean here?
Yeah.
No, this is for a given value of J, say you give me J equals 1. I go from -1 to 1.
Okay, sorry, I thought that was 1/2.
The alpha you only need for the continuous part.
On the non-normalizable state, there should be a delta alpha alpha prime also.
Yes, it's also here.
And in the normalizable state, there's still a delta function in J in the norm.
But no, You don't need the delta function J. I mean, you have you see it like you see when I write the 2-point functions. There are
Yeah,
some.
you did write it for the.
Yes.
Will write now.
So what I mean is that these are normalizable in the usual sense.
Normalizable and
Yes.
the other one is
This one will look more like a parameter.
But you said J is still a continuous variable.
Yeah, J can be so. Let me get to the 2-point functions and then we'll see what the difference is.
I mean, J is a continuous variable when you look at the representations of SL2R. Once you embed in string theory, J is no longer continuous because there is another constraint, the Virasoro constraint, that restricts it to take some discrete.
So just for SL2R, which is what I'm doing now, it's allowed.
Yeah, he's doing just for SL2R, for him J is
Okay. So this was one kind of classical analysis in the quantum theory. You have vertex operators, EJM. They're going to be something like this. For now, again, gamma is function of z, and if I'm not in the interaction near the boundary, it's actually a function of z at the bar, right? You get something like this in my conventions, and something like this. So this is the state, the operator, that when you act on it at 0 on the vacuum, it's going to create some state Jf. Okay? And you can check that if you use the OPEs of the Wakimoto variables and you act on this, you get the actions that you expect. For example, if you act with J plus acts with beta. Beta is basically a derivative with respect to gamma, so that lowers the value of the exponent of gamma, which takes m to m plus 1. Okay? Fine. And then I have an x-basis representation of the same guy. In order to get it from here, I just have to invert the transformation that's over there. So, roughly speaking, you'll understand this is strictly true for the discrete series, and for the continuous ones, it's a bit more subtle, but you can write it as this. The sum over all the allowed values of m and m bar is jm. Sorry, I'm missing it. Okay? So this is the quantum theory, this is the Wakimoto representation of the vertex operators. And you see here that this already tells you something very nice, right? Because we know that x, this x here, is the insertion point. At the boundary, right? So this means that this guy, actually, strictly speaking, is when you integrate over the worldsheet coordinate, but that doesn't do anything very interesting here. This guy is what I want to identify with some local operator O or H, where the weight is J inserted at X of the holographic CFT. Okay? And since now here I'm expanding in powers of the worldsheet coordinates, this tells you that these guys, which were the energy eigenstates, are exactly the Virasoro space-time Virasoro modes of this operator. Okay? And you can check if you take the space-time Virasoro generators that we defined at in the first part of the lecture, and you can check that if you act on this, you get the action of the differential operators, but if you act on this, you get with the non-trivial, with the modes with the non-zero index, you get exactly what you expect from the Virasoro modes on the boundary. Okay, what you see in chapter 6 of the Big Yellow Book. Okay, this is exactly the modes, the space-time modes of the operator, and this is the local operator on the boundary. But at the level of the worldsheet theory, M and X are just labels of the solution, right? Of the operator. Okay. And now we have to move into, I said quantum theory, okay? Quantum theory is the quantum version of the Wessel-Witten or the Cosette model on H3 plus, or the Wessel-Witten model by the way, having M being, so if J is real and N is some natural number, M is real as well, and M bar are real as well, for example. And this makes sense because we are thinking of M and M bar in the Lorentzian setting as the energy and the momentum, right? You'll find that in the original analysis of the H3 plus model by itself, the Euclidean model by itself, the natural way to take these M's is to take the M's being complex, being imaginary. And that's why in the H3 model, these normalizable states are not part of the spectrum. You just have the continuous ones, which is the same as you would have in Euler theory. Okay. So now, okay, I did the quantum theory in the sense of the H3 plus model. And now finally I want to get to the string theory spectrum. So as usual, I want to take my string theory to be on AdS3 cross, or the Euclidean AdS3 if you want here, cross some M internal, right? And I need to impose the Virasoro condition. So the Virasoro condition looks something like this. So this guy, I didn't say it here. If you work with any of these guys for any value of M, in all cases you get that the weight depends only on J, and it looks like this, which is the quantum version of the mass in the Laplacian equation. And then you need to add the internal weight, and then you need to add the descendance level, and add the -1, and that needs to be 0. Okay? This is the Virasoro condition on the worldsheet. And now I have a problem, right? I have a problem because both of these states that are in the spectrum that I just constructed are going to be problematic in the usual setting. Why? So I have two problems. So the first one is if I look at the continuous sector, again, continuous is maybe a bad word, but the delta function normalizable ones, I have that J is 1/2 plus I by S, which means that minus J minus 1 is 1/4 plus S squared, right? And then if I plug this in here, I see that I have a positive thing here as long as K is larger than 2, and the internal weight is larger or equal to 0, which is what you expect if this guy is compact. Then compact and unitary. Then these two conditions, I have a positive thing here. From this, I have a positive thing here. N is the descendant level is positive. So for n different from 0, there is no solution. Right? I can't solve the Virasoro constraint. And this is exactly the same thing that we saw at the classical level. These are the states that correspond to the space-like geodesics, space-like particle geodesics. Are what right? That should not be part of the spectrum. Have no of the string theory spectrum. And also at n equals to 0, you might say, okay, maybe there's a state there. But what happens is that if you go back to the Laplacian equation and you look at the mass, and now instead of looking at it in units of alpha prime, which is what I was doing, you look at them in units of the AdS radius, which in this case is the square of the radius is k. So if you look at the mass for this, which is a function of j, so k times the mass, this gives you minus 1 over 4 minus that squared, right? Just looking at the formula I had before and identifying the mass, which is always smaller than minus 1 over 4, which is exactly the BF bound. Okay? So there is also no solution there because these things are tachyon. So they're not part of the string theory spectrum. So I just travel to construct the delta function of my isomer states, and now I have to throw them all away. Okay? And the second problem is that if you look at the discrete sector, you see that you need j to be larger than 1/2, but in the end, you also need this to be, at least semi-classically, smaller than k over 2. And the reason why you need this is because in the, well, roughly speaking, in the Malacena Oguri paper, the third paper, let's say, in 2001, they show that they can prove a no-go theorem, but the proof only works for j smaller than k over 2. Okay, and one reason why this happens is that at k over 2, you hit a null state in your representation, your affine representation. So in particular, for example, this null state, which is j minus minus 1 on the guy which is j equals k over 2 and m equals k over 2. Okay, so this is the null state. And this can be shown very easily because if you look at the norm of psi, then you just get something like this. So here I have to put minus minus 1 k over 2, k over 2. And here I have to put the conjugate, and in the conversions I'm working on, this is plus and plus 1. Okay? So now I use the commutators between these two guys, and you show that this is exactly k minus 2 j03. Right? I just commute these two, and I get a central term which comes with a k, and then just the usual commutator between plus and minus with index 0, but this has exactly eigenvalue k over 2, right? Because the m is k over 2, so this is 0. Okay, so I have a state which is a descendant. That's something that seems a reasonable primary state. I have an affine descendant at level 1 which has norm 0. This is where I start having problems, and this is ultimately, in some sense, why you get this type of restriction, right? So, okay, this may seem fine, but the problem is that we identified the space-time weight with the value of j, right? So this means that I can only construct operators which have weight smaller than k over 2. And this makes no sense. It makes no sense because the central charge of the theory is way larger than this, right? And I know that I should have other operators. In particular, in the supersymmetric setting, you know that you have a huge number of chiral primary operators that are above this bound, right? These are not typical bounds. Okay? So I have two problems. I need to construct states that are that have weights that are larger than this. So the problem is how do I construct states with this being larger or equal to k over 2? And the second question is, what are the string states, right? What we call the string geodesics, the long and short string geodesics. And the answer to that, and this was a puzzle for some time at the beginning of the story, and the answer to that is that, as in the classical state, you need the spectrally closed state, which are by far nothing that you would usually consider in the original H3 model. Right? At the level of pure Waterman-Witten or Cosset model on H3 plus, this story, you don't get the normalizable states, you just get the Liouville type states, and that gives you a consistent spectrum, and that's fine. But at the string theory level, it's not true. So you need to consider more states. And this is what Maldass and Aguri understood, is you need to include the spectrally flowed states in the story. These are going to be both the short strings and the long strings that we discussed in the first lecture. What time?
But if you were in the bosonic string,
Yeah.
what goes wrong here? If you have an extra.
I'm in the bosonic string. I know I need the central charge is way larger. I still expect to have states which higher space-time weight. It's not the so obvious ones as the chiral primaries, which are kind of universal. But if you just look, for example, at the in general, if you look at the run at some whatever you would call the holographic CFT, you're gonna have anything that you can hook up with this central charge and the right properties, you're gonna have more operators on this.
So it's not that you're going to get the Ramon states.
No.
Also, your worldsheet Torus partition function is not going to be modular invariant.
Yes.
If you keep only the states that he has written.
Way of saying that there's something inconsistent. Okay, so do I have 5 more minutes? Okay. Let me introduce the basics of what I'm going to say. The idea, if you remember the spectral flow that we had in the first lecture, the idea is that you have a family of photomorphisms and which now in the first lecture we were working at the classical level, so we were only looking at the zero mode, right? But this extends to the full affine SL2R. And what you get is that if you define currents that look like this, then these guys here satisfy again the same SL2R, affine SL2R algebra. Okay? And so there are two comments here. First of all, why do you get this shift in the modes? Well, if you remember the first lecture, we had that J plus or minus tilde were something like e to the I tau plus sigma, something like this, right? So we had the sigma plus, and you have the plus minus in the exponent, right? So now this becomes, in the complex notation, the Euclidean notation, it becomes a factor of z to the omega, and having a factor of z to the omega exactly shifts the modes in this way, plus minus omega. Okay, that's why this translates into this. And the argument is that here you see that you need omega to be integral, right? Otherwise, it makes no sense. Okay. And so the thing that you're going to need to add we need to consider not only the primaries with respect to the currents J, A, N, but also the primaries with respect to any possible current with a tilt. Right? So something that is a primary under these guys, under these guys here, and but not under this one, because I'm shifting the modes. Right? So if the positive modes here annihilate some states, then that's not going to be true here. You're going to have, in particular, the J minus shifts downwards, so it's annihilated by some negative modes, and the plus shifts upwards, so there are some positive J plus modes that are not killing the state. These are the states that are going to contain the short strings and the long strings. Okay?
You should do this for every integer omega.
Yes. And to actually show exactly what happened to them, I think it's a good point to stop here and start with that next section.
Maybe, I mean, sort of naive, but you have a sort of incarnation of AdS3 already in your switch from the M to the X basis, which from the string point of view is like nothing but a change of labels. But
the X basis, I mean, already for the H3 plus model before thinking about AdS3, that was useful. I mean, it's already useful. You cannot. It's the isospin variables in the SU2 case.
Yeah. So my question is more like, so I also have these two bases if I go to higher dimensions, right? I look at H4 and I start looking at the Laplacian equation just like you did, and I start to build.
Yeah.
So is that also like just naively like your sort of first incarnation of AdS3 in a higher dimension, that there should be some way of seeing this from the
I would think that there's some analog of that, yes, but in general, I don't have a working theory.
Of course, you can't make it as precise because now you're really getting into the details of like, okay, I'm building the spectrum, and for this I need, like H3 or SL2R.
So at the level of the solutions of the Laplacian equation, I would say yes. You can probably do
could
it.
sort of like, okay, I'm just curious. Yeah, morally.
I think yes.
Not completely.
At the quantum level,
So what is M5 in on this story?
N5 is K. The bosonic setting is K.
Ah, okay, sorry.
And so the float states, can you have a classical? Do they have a classical analog?
The string geodesic.
Yeah, but if you try to construct the analog of the V that you had before.
Ah, yeah, it
is where.
So the easiest way to do it is to shift. Yeah. Yeah. You can see it from here. You have to shift the value of M. So you're gonna have some extra Z omega in front, and you're gonna have some shift in phi as well.
So there are still some functions on AdS3.
Yes, but
But why didn't we find them then in the beginning? That's the question.
because the fact that you need to add some z omega factor in front means that if you just restrict probably to solutions which are, so if you take the gammas that are being independent of z and z bar, as we did, they're probably hard to see in that limit. You see them if you look at geodesics, but if you, I don't know how to.
But in the classical solution, they had to depend on the worldsheet coordinates, right?
I was surprised.
In the last lecture.
For the wave function, yeah, in the first lecture, yes, but for the actual wave function associated to operators, I try to argue from the King's homological equation. If you remember, for the correlators, you had something like this. You had a bunch of stuff on correlators, right? These guys depend on the worldsheet coordinate, but at infinite k, this disappears. It says that this whole thing has to be independent of z and z bar. So what you would like to call the wave functions of these guys, it's hard to realize them with that. Of course, this is not true for spectrally float states. The King's homological equation is different because they're not affine primary, and you use that in the derivation. So by restricting to just seeing the gamma and gamma bar and phi as just coordinates, I think they become hard to see. But there is probably
It's just the
another.
index was too restricted.
There should be a nice way to see them.
You think that somehow could I see them from just the eigenvalue problem on H3? Like
as we set it up,
classified. Like,
as we set it up, no. But since they're there as geodesics, right? As classical geodesics. Again, the classical geodesics were not independent of that part. These are really the geodesics, not the wave function of the. You can do the same game with geodesics in this Euclidean context, and you get these tubes, right? But at the level of wave function and solution of the operation equation, as we set it up, they're not visible.
I think you will never be able to see it from the Laplacian because Laplacian is not using the fact there is B field at the worldsheet or in the space-time. Sorry, it's only relies on the. So if you don't have the B field, I don't think this winding will come. It's how to say this thing. This is
it's a balance the gravitational
Bohm effect. If you have an electric field and once you cross the center, if it's not rotating by 2 pi, integer multiple of 2 pi, it's not mutually local. So it's not come back to the same point. So I'm not explaining it right, but one way to see it in the M basis, I think is very easy to see. You just look at all the operators and you will see that you are missing some operators. So the Laplacian, I don't think that you will see it.
There might be a way to set up a classical computation. Yeah. That's still.
There's one more problem with the Laplacian because these are like local insertions on the boundary, right? But when you have a winding, they are no longer local insertions on the boundary. They're extended objects in some sense.
So in the Euclidean setting, you can see the kind of winding around one point.
Yeah, that's what he drew, right? With the like at the very beginning, there was a graph here where like it was a point insertion with some omega.
Yeah, but then you have to fix gauge that gamma is equals to z to the power omega or something like that. And in a very particular case, maybe it's okay to maybe it's possible to see.
Yeah. I would think you could then also include the B field in the eigenvalue problem somehow, but like should
not in the Laplacian.
But not there, but like you would do a more general. Okay, you would.
I was just trying to.
Some covariantization or whatever, like I don't know, like not just the scalar Laplacian, but like something a bit more general. Yeah, that would take into account the BG. I have no idea how to do this in practice.
I never tried. I think it's possible. You would probably need to take into account that you have a B field as well.
Yeah. And one important thing is that this winding is not a conserved quantum number. So it's not natural. It will not naturally arise in like whatever eigenvalue problem that you want to set up. There is something that you have to put it from outside.
Yeah, it's still a label on your state.
Yeah.
Yeah. So what I try to do here is to follow the kind of historical route of the. Like, people try to take the H3 model, right, the Euclidean AdS3, and to just say, okay, I take this, I do some analytic continuation, and I get to AdS3. That doesn't work. It doesn't work for this reason. I never tried to do exactly what you were saying. It might be possible, but I honestly don't know.
No more questions?
Okay.